For my second presentation, I shall be discussing a physical model that I've built in cooperation and collaboration with Eric Dollard. Now, this idea behind the project was to ultimately configure and represent what is being practiced in some parts of the for a large part of the utility system of the double Y connected transformer and other various transformer connections for that matter, along with other loads and how that affects. Now, the basic transformer overview, I won't go into much detail about this, but this is the traditional way of how it was set up. Now, in my area in Los Angeles, this is how it is actually until this day. It's a delta-delta bank, about 12,470 volts, but we could see that it's on racks, it's sturdy installation, and the characteristic 3 and 3 wires. Now, this is a more modern adaptation of what's being practiced in parts such as Pasadena and other places in California. Now, it's still delta on the primary, yet they've transitioned to Y on the secondary for lighting loads, and it's still 12,470. Now, this is one of the most popularized and most practiced configurations as of now. And then this is the abomination that they're practicing. It's a YY connected transformer with the neutrals of the secondary and primary tied together, and some of them, the neutrals are even tied together by means of grounding. Now with this, we have a diagram, pictorial diagram schematic of we have the polarities here, but the overall configuration of Y. And in this case, the neutral isn't tied together, but when it is, third harmonics and zero sequence currents through the neutral are able to flow, make their way throughout the distribution system. Now here's just a influence of the harmonics. It's showing the fundamental third harmonic and the disruption. Now here we go to the physical model that I've been able to construct. So the attempt number one, was to find a suitable generator that produces a three-phase signal of considerable magnitude, not too high that you cannot handle it without having to properly or really insulate your setups. But the control transformer or Selson control transformer was recommended to me, and that it has a field excitation coil as seen here, and it's able to produce a relatively clean three-phase signal, though the rotation of the Selson, since it's 3 poles, you would have to rotate it at a considerable RPM so that to get 60 cycles. But since the way it is built, it's not built to rotate, you cannot drive it more than 1200 RPM or else it's pretty much going to destroy itself. So what I was using to drive it was a Jensen steam engine, which was pretty practical at the time. And I used a belt connected to the flywheel to the generator, and this spun the generator, producing about 30 cycles. Now, it's not ideal, but it was better than nothing. But then, unfortunately, the final results were that the total impedance of the coils within the control transformer were too high, and thus the power produced, it could not be stepped up by the transformers or the transformer substations, as I like to call, which would step it up to the high side and then step it down to the consumer side. It would only put out a few millivolts. So that was an unsatisfactory result. So I had to dig the web and see what my other options were. Now I went to attempt 2. Now this was the best I could do. So I found these individual three-phase generators. They're fairly small, but they're not exactly ideal because it's not producing a 60 cycle sine wave, rather a 131 cycle sine wave. So that's really high up there, but it's good for this manner. Now this I used driven by 2 DC motors that would produce a combination of 3-phase. And this was all mounted on a sturdy board so it doesn't vibrate and move, because it does vibrate like the Dickens and it starts moving across the table when I turn it on. And this is the overall setup. Now I have a DC source connected to the motors that spin these 3-phase motors, which produce enough power at 7.2 volts, about 11 milliamperes. And this gets fed into the transformers that are pictured up above right there. And then we have the sine wave quality results of the various transformer configurations. So this is the generator oscillogram without anything connected to it, just the oscilloscope. This is the sine wave it produces from one phase to the other. It's fairly clean, not completely. We see that it's a tad distorted. And then we have here a wide delta network with a load here, incandescent bulb, which dampens the amplitude of the sine wave. And then here we have a nonlinear load, such as I actually use 2 LEDs, which completely distorts the bottom half of the sine wave. And then in a delta-delta network, where it's a completely closed system, we have the incandescent bulb loading here, and then we have the difference of the LED nonlinear loading. But we could see that there's pretty much no difference between the two. Of course, the sine wave is not clean. It's a little odd, but nevertheless, we see that in the delta-delta network, none of these harmonics could be generated or propagated throughout the rest of the system.